Hi, my name is George Yule, author of Quantum Theory of Time. In this video, we will explore the entropy you think you know and the entropy concepts you really need to know. Entropy as a concept was developed over the 19th century. In 1856, Clausius was likening it to a number of objects. His original line of thinking is very concrete. If I have a plate, it will naturally break down into pieces, and therefore the multiplicity of the universe increases. A decade later, in 1865, he termed this entropy, and this is the term we use today. What you think you know about entropy is only the tip of an iceberg, if it even describes entropy. Entropy is a measure of individuality as a form of energy, so it is also a general type of space. It does many things relative to context. As such, the only way to properly understand it is to take a quantum mechanical approach. If you had chemistry, then you learn entropy is the mechanism in heat for the phases of matter, not temperature. As enthalpy stages, part of the energy must apply as entropy before temperature can continue to increase. As real energy acting on the system, entropy gives atoms their own field space to push away interactions with other atoms. Space is local and flat. Entropy is general and angular. It is a function of the field, enabling individuality, at least in this context. This is a polar graph showing circular functions relating the opposite perspectives of temperature and potential to each other. Everything in the area of cosine alone is a solid phase, meaning all the parts move together uniformly. In terms of the phases of matter, the orange-filled area where sine and cosine overlap is the realm of liquids. On the potential end is gas, where all the parts move freely. Temperature and potential cannot be directly connected without asserting a magnitude of individuality. Magnitudes are scalars, meaning numbers without units, and individuality is entropy. The scalar measure of individuality is the tangent line. As a heat function, the scalar is reconditioned by Boltzmann's constant to make the axes compatible, and the z-value shown here is the redshift form of entropy. Redshift and a broken plate give the illusion that entropy always increases. This sounds good until you think of an ice machine. This is the original real-life model of an ice machine made by Jacob Perkins in 1834. It works by converting stored energy called enthalpy into heat that is then carried by either emitting or as infrared radiation, or by reapplying it as enthalpy to other atoms that then carry it away. We didn't need a device to reverse entropy and make ice. All we had to do was wait for the right weather and watch entropy reverse itself. It doesn't take much to break this initial idea of entropy always increasing. This isn't to say the rule is wrong, only that it has a limited application. You have to be careful not to overgeneralize some things. This sent Clausius back to the drawing board to determine how exactly does entropy reverse. His answer was angular momentum. Angular momentum curves into local position. This is why in special relativity, the inertial frame is angular and cyclic. In 1873, Clausius devised his virial theorem measuring the angular momentum among a group of moving bodies. At the bottom right here, you will see Newton's inverse square law converted into virial theorem. Notice that local masses are excluded, so this is only measuring the kinetic energy. Kinetic energy is the energy of motion. In 1933, Fritz Zwicky applied this to the Coma cluster of galaxies. The kinetic energy he measured was 100 times that of the parts measured separately. He called it dark matter. And popular thinking has chased the idea of an exotic form of matter ever since. This kinetic energy belongs to the next order of matter. Since he was looking at galaxies, then the next order is the cluster itself. There is no mystery exotic matter defined. It's the inertial frame of the next level of generalization. All the popular mysteries of physics are solved with a better understanding of the applied established physics. Applied physics is more fun, to me at least, because it helps understand how the universe actually works and gives you things to play with besides ideas to nowhere. With virial theorem, Clausius now evolved his views. He realized entropy is complex. We can confirm this with the range of other ways to measure entropy, such as microstates or energy density. These ideas are not in competition. They complement each other, making them equivalent from different perspectives. In quantum mechanics, we see these as empirically valid and subject to contextual influences. In other words, each approach becomes a probability relative to a context, and all may be simultaneously true. This is the concept of complementarity in quantum mechanics to come over 50 years later. So, needless to say, when Clausius saw how slippery this stuff was and recrafted his second law, he redid it to the language you now learned in grade school, which is to say energy flows from high to low potential. It sounds easy until you try to comprehending what that actually means. So now we acknowledge heat and therefore entropy are reversible. We start with a solid. Temperature in a solid applies to linear volume among the parts. Alone, it does not change the phase. The phase here is uniformity. There is not enough entropy to interfere with the parts relating to each other. Each pair of parts relate directly with their neighbors. Oppositely, a gas consists of parts that have no connectivity to each other. They can be in a closed system that itself is connected to them, but they have no interactive influence apart from rejecting each other's influence. What prevents this is the angular volume of entropy. Entropy has shifted uniformity from a general perspective to a local perspective. So the question is, how? By adding entropy to the general system, we have lost the ability to act on the whole as a uniform thing. We now act on the parts separated instead. Each end works towards the middle. As we enter the enthalpy range, we retain the current state until the energy of the system in total achieves the necessary threshold. Then the nature of that application is as entropy. Liquid in the middle has a one-way statistical level of individual connectivity. With a solid, the connectivity went both ways. Here, the total connectivity is less than 1, but not 0. At 0, it's a gas. The fluid state is basically an exception in the middle between completely connected and completely disconnected. I introduced complex variables I and j in the dual numbers in the first lecture on time. So far, we have described entropy in space as real work value. Real work value is exactly conserved, meaning you can and must follow it directly through its transformations, and it is never created or destroyed. Now we need to add a complex treatment of work value in which we distinguish real value from available emptiness. The J operator here consists of both real and dual number parts, where the dual number defines a useful emptiness. When we get into the solid phase, we have no real entropy between the atoms. They are now uniform to the generalization we call ice, at least with water. The dual number here takes over as describing the individual atoms despite their uniformity as ice. It also divides the atoms into their parts. By reducing this useful emptiness, we can change the state of energy. It is this specific value that we need to reduce to change atoms into gamma rays, and is the goal of such research looking to develop gamma ray lasers. The goal is to achieve at room temperature what is otherwise required to rob the temperature all the way down almost to absolute zero. Absolute zero exists when you are observing just the entropy axis. Otherwise, you're trying to negate space entirely. You can't. With a solid, temperature is the linear thermal expansion among the parts, but it does not interfere with their connectivity or sense of uniformity. Temperature is also subject to a complex I operator, especially at and beyond the enthalpy of vaporization. As with complex entropy, complex temperature has real and useful empty parts. Useful emptiness is low potential. The background provides freedom as useful emptiness for propagation and motion. The greater the degree of useful emptiness, the easier it is to pass through without interference. It affects the phase density. Obviously, these useful emptiness variables apply outside the ranges shown, but within these ranges, they dominate. When I say space-time geometry, I mean the construction of position. We will get to this kind of space-time geometry much later in the book. This includes features of shape like surface, volume, and the features of function like mixing to establish individuality. Connectivity begins with defining position. Each position has 4 geometric features defined generally in the first law of thermodynamics. These are paired, so temperature and entropy are the relationship with the field, and pressure and volume are the spaces of position. Each pair has a real part and a usefully empty part. One member of each pair is linear, and the other is angular. Entropy is a vital concept throughout this. For now, our only concern is introducing entropy in its most familiar form as a feature that enables us to act on a position, and for the position to act on other positions. It is a virtual axis, meaning it is a usefully empty container. Let us start with a volume and a surface separately. These separate features are called manifolds. They take on specific shapes when given context. I show them in convenient round shapes, but if you ever dissected a ball, you know this is not how tidy things are. As functions of the field, these lack position, and without position or some reference, they're just free energy. A surface by itself has a radius twice that of a volume it would cover. Combining them causes them to apply boundaries to each other, reducing the collective radius and density to the volume contained by the surface. For the sake of general relativity, this generalization fits the model for gravity describing a surface acting on a volume. Unfortunately, layering alone does not establish position, but it is a generalization of weak mixing. We will come back to that mechanism much later. Thanks to mixing, we get an entropy function containing the surface and volume. Now that we have an individual position, we can apply temperature. Temperature is the linear space around the identity, so long as the virtual entropy axis doesn't get filled by real entropy. It has to remain available for all interactions. This temperature is not assumed here to be emitting or pushing everything around. Without entropy enabling division, it is just expanding the local realm. This is known as linear thermal expansion. This energy can also be converted and applied in a kinetic form. As a kinetic form, it applies force causing linear motion. Linear motion in physics is called translation. Translation applies when the virtual entropy axis is full of real entropy enough that a temperature axis, given direction to make it a vector, can act on that position directly, of course with equal and opposite effect that it moves. Paradoxes are contradictions in our minds. In reality, they are ways to make otherwise passive things active. Each pair has a real work value and a dual value. Each pair has an angular axis and a linear axis. Space is local and entropy is general. These rules can appear to be reversed, especially in contexts where they can swap rules like CMB or heat. To be confined in position requires the local flat space to be curved. The entropy around a position is in degrees of curvature, ironically toward flatness. The floor or table, as an example, seem flat but they have an ever so slight bit of curvature to them. When we release space and entropy from their degrees of curvature, they go in the opposite direction. Space unfolds and oscillates like a leaf spring as it smooths onto a general surface. Entropy, conversely starts as a relatively flat surface, then diversifies. As it diversifies, it increases its curvature and enfolds rather than unfolds. It is enfolding into even smaller wavelets. Both space and entropy are passive in their preferred forms. They're standing energy. What makes them active is the degree of curvature out of their preferred form. They're never in their ideal form, but they do get close when they're finally able to interfere to form CMB. There's an ages-old philosophical debate over free will and determinism. We shouldn't be having this debate. You need a proportion of both to function. Complementarity applies in all its valid interpretations. Empirical methods in computational practice are very deterministic, so a rigid habit has formed in physics. It was this rigidity that Planck showed makes it impossible for the classical approach to be complete and necessitated the methodology of quantum mechanics. Entropy gives a statistical measure of independence. At the point of wave collapse, freedom is achieved. As the number of possible states increases, so too does the degree of their independence from a greater whole. We can see this in society as increased population makes it harder to act uniformly. If your bones are determinism, then your soft tissues are the free parts. The combination in proportion and connectivity are what make you functional. Without the proportion and connectivity, the free and deterministic are worthless. The universe is no different. It has hard parts and soft parts, and they work together. When they're separated, they cease to be functional. The universe is object-oriented, and it processes local to positions, not collectively in general. This local processing is why studying the field is so hard. Positions group into populations. They are hard and real. When you put a population into a context, that context brings its own scale of perspective. We can now mathematically analyze it. Let's assume we know a proportional relationship like pi being the ratio of a circumference to a diameter. To find our significant digits, we apply a very simple function. Our function gives digits as an integer, so we have to round our results. The 2 here is a landmine that we'll come back to in a bit. A logarithm gives the exponential value to a base, which here is the relative proportion. The presumed base of a logarithm is 10. The base of a natural logarithm is Euler's number e. To find the logarithm of another base, apply a standard logarithm to the population being computed and divide by the same standard logarithm applied to the intended base. Now let's throw numbers at this and see the damages. Let's say we're drawing a circle. How wide do we need to set the projector? 3 kilometers is 3 meters, and let's just start by assuming we're able to use a meter stick because we're in the real world. If we were on a map with a legend scaled to kilometers, then we only have 3 significant digits on that map. Let's forget about that map and do it in meters. If we take the logarithm with respect to pi of 3000, we get 6.994. Add 2 and round to the nearest integer, and our margin of error begins at nanometers. That is billionths of a meter. A nanometer is just a little smaller than the radius of DNA. That's pretty small by our standards and not a huge amount of wiggle room. Now, recall our 3 kilometers. If it were only 1 kilometer, then it is a unit perspective with only 2 significant digits. Let that sink in a moment. And remember back to grade school when they told you to just use 3.14 for pi. They were reducing the value of each circle to a unit, or leaving a potential margin of error in the results by making the problem easier for you. In the real world, you have to be careful with this, realizing this it is common in practical application to round up and cut a little long just to play safe. Now let's compare different contextual rates on the same population. Each rate has vastly different significant digits. I picked an arbitrary 5,000 for the sake of providing an extreme example on the verge of breaking down the system. It has greater freedom than the other due to fewer significant digits. It is easier to fudge, squeeze into, and break down. Significant digits is inverse to our traditional handling of entropy. It is measuring general uniformity, not local freedom. By applying Boltzmann's constant here, we convert it to the energy-compatible form. As the number of digits increases, our degree of freedom decreases. Conversely, as it decreases, it approaches that 2 I warned is a landmine. It's a landmine because it hides a function holding local identity together. As we approach it, we're near a point of system breakdown. Now about this landmine. The number 2 is a generic minimum. It is our unit boundary condition for virtual entropy. The population consists of local identities. Each identity is contained by its own virtual entropy, which this number represents. We assume it is 2, but really it is a function of the relationships forming a local identity. Those relationships are mixed, and mixing comes complete with its own virtual entropy measure. This is the quantum mechanical number with a weak mixing angle. That, too, is a generic perfect mixing angle on the boundary of wave collapse. That midpoint has a value of 2 for the secant squared. You will see this secant squared again when we use Hooke's law in conjunction with weak mixing to establish the massive position. When we go below 2, we're crossing over from a general to a local perspective and then dissecting that local into more fundamental parts. On our circle, we round pi up to 3. We will always have problems and always be short of a complete circle. We break the system by rounding to anything less than 2 digits. It isn't that we broke the laws of physics, but rather that we are breaking down from one perspective to an even lesser set of perspectives. One is wave collapse for functions of the field, and 2 is wave collapse for functions of position, like this and Lorentz factor. Wave collapse means the nature of identity has been compromised by losing an axis giving it one form of connectivity, which is replaced by another axis showing another form of connectivity. Or it is not replaced, resulting in an absolute freedom from position like background temperature. In terms of the phases of matter, wave collapse is a change in energy state instead of a change in phase. One possible result is a Bose-Einstein condensate. Basically, the atoms lose a level of internal diversity, causing them to break down, lose their identity, and become a function of the field. The greatest paradox I saw in wrapping my head around space and entropy was realizing they're the same thing from different perspectives. In CMB, the real space and entropy axes are the plus and minus B modes. What helped me see this was dissecting the spectrum to see how space worked on one end versus entropy on the other. Spaces are excluded in some way, even with ordinary light, where electrons quantum leap to exclude photons. Long waves, conversely, are generated by the field and charge interactions of various types. Either way, the propagation consists of a real value that can do work in the right context. It also consists of a useful emptiness in the form of information or diversity. Virtual axes are proportionally conserved, so losing an amount of diversity in one perspective creates a greater degree of useful emptiness in another. As long waves reduce to wavelets, they ironically increase their receptivity to a temperature axis. Conversely, the smoothness of a heat surface has a very low receptivity to entropy. The combination makes them compatible with each other to fill each other's useful emptiness. The dual number value for each then generalizes as an E mode. The really baffling part of that is how we normally think of entropy, which is really more similar to the virtual form of entropy than the real form of entropy. But it is back here with this initial handling of entropy that we can see why we get confused. Again, Clausius began with entropy as a tangent function. That tangent function is actually uncertainty principle, shifting and thereby connecting opposite perspectives of position to the field. At the quarter angle, we hit wave collapse, where the directional and relativistic effects of local position no longer apply. We're now in the realm of the free to go every which way, which is why we call it uncertainty. Uncertainty generalizes the virtual axis, but beware, we're working with dual numbers. A dual number squares to zero. We cannot apply one virtual axis to another without negating both, which is why at CMB the virtual axes cancel and generalize to E mode. Now, this is conserved, but in a different way. It is conserved proportionally. So the proportion of the useful emptiness just changes roles. It was because of these paradoxes with entropy that we needed to distinguish potential, defined by dual numbers, from work, defined by real numbers. Understanding space, time, and entropy requires the quantum mechanical reasoning concepts of complementarity, uncertainty, and correlation to the reproducible facts. Please be sure to like, subscribe, buy the book, leave a review, and stay tuned. Thank you.